Welcome to the deep dive. This is where we stop just skimming the headlines and really start mapping the intellectual terrain.
And today, the terrain is, well, it's about as monumental as it gets.
We've brought in a pretty deep stack of sources today. We're looking at university physics lecture notes, rigorous empirical data from particle detectors, and some really complex geometric descriptions of the cosmos itself.
We are, I think, embarking on a journey that fundamentally redefined reality. It's what forced physics out of the comfortable classical 19th century and into the modern era.
Yeah, our source material covers the entire arc of Einstein's work. I
Yeah.
mean, from the first cracks in Newtonian mechanics all the way to the geometry of black holes and, the expansion of the universe.
And our mission really is to trace the lineage of a single, simple, but just utterly subversive idea.
Which is that the speed of light, t all hours, is invariant. It's the same for absolutely everyone, no matter how fast you're moving.
And we're going to unpack step by step how that one constant forced physicists to just completely tear down and rebuild their ideas of space, time, energy, and ultimately gravity itself.
Okay, but before we dive in, we have to get our vocabulary straight. These are drawn directly from the source materials, the foundational concepts.
Right, let's start with three key ideas, because without them, none of this makes sense. First up is the event.
The event.
An event is simply something that happens. It happens at a precise point in space and a precise point in time. It's a single location in what we'll eventually call space-time.
So like the classic example from the notes, a piece of chalk hitting a professor's forehead.
Exactly, or a photon hitting a detector. The really critical thing about an event is that its reality is, well, it's independent who's looking. All observers, no matter how they're moving, have to agree that, yes, the chalk hit the forehead. That moment occurred,
Which brings us directly to the reference frame.
which is your personal system for labeling that event.
It's my coordinate grid and my synchronized clock. So if I'm in a control tower and you're flying past in a shuttle, we're using two different reference frames to describe the same event.
Precisely. And that leads to the third and maybe the most subtle concept, the geometric object.
Okay.
A geometric object is something with physical properties that exist independent of the reference frame you use. Classically, everyone thought the length of a ruler was a geometric object.
Right. It's a meter long, period.
But as we get into relativity, we're going to find that a lot of things we thought were geometric objects, like time intervals or spatial length, are actually frame dependent. They change depending on who's looking.
So the whole goal of relativity is to find the true geometric objects, the things that don't change.
That's it exactly. What is fundamentally real for everyone?
Okay, let's start where physics was before all this, before Einstein, before Maxwell even.
Yeah.
The very comfortable, intuitive world of Isaac Newton. What was that classical starting point?
Well, we were living under what are called Galilean transformations, and this framework was just rooted in common sense. The absolute cornerstone was that time was absolute.
Right. If a lightning strike happens, my clock and your clock, no matter where we are or how fast we're moving, they both tick forward at the same rate. We agree on the time, $2.
The time coordinate is the same for everyone, TP equals TC2. Full stop.
So if an hour passes for me, an hour has passed for the entire universe. And space was, I assume, just as straightforward.
Oh, yes. If you're moving relative to me at some constant velocity, $5, our spatial coordinates just shift in a really simple linear way.
Oh.
My position, $6 is just your position, $6 plus your velocity times time.
It's basic velocity addition. If I throw a ball at 50 miles per hour on a train that's moving at 100 miles per hour,
Someone on the platform sees the ball moving at 150 miles per hour. Speeds just add up. Displacements and speeds, they all vary between frames. It's all intuitive.
and it seems to work perfectly for everything we experience day to day.
It does. And what made the system so stable, so powerful, was that it guaranteed the laws of motion were consistent for everyone. Critically, acceleration was invariant.
Okay, so even though we disagree on my speed, we'd agree on my acceleration.
As long as we're not accelerating relative to each other, yes, my measurement of the ball's acceleration would exactly equal your measurement. And that was the bedrock. That was the stability of the Newtonian universe.
Absolute time, invariant acceleration, simple velocity addition. Everything was neat, tidy, and about to be completely broken.
Right. And the person who broke it, without even trying, was James Clerk Maxwell in the late 19th century.
He synthesized all the known laws of electricity and magnetism into one, beautiful set of equations.
And that synthesis opened the conceptual crack. You see, physicists at the time really understood wave equations. They'd studied waves on strings, sound waves in air, ripples in water.
And the classic wave equation always gives you a specific wave speed, $.
But, and this is the key point, that speed is always measured relative to the medium. The speed of ripples is relative to the water. The speed of sound is relative to the air.
So if I'm moving relative to the water, I'm going to measure a different speed for the ripples.
Exactly. But then Maxwell's equations for electric and magnetic fields, they also produced a wave equation. And this equation was stunning because it predicted the speed of these electromagnetic waves, light using only constants from static lab experiments.
Let's really drill down on that because it's just incredible. Maxwell's theory said the speed of light, $2, was fixed by two numbers. The permeability of free space, $2, and the permittivity of free space, epsilon dollar.
And think about what that means. You can go in a lab and measure epsilon dollars with some static charges on metal plates. You can measure a level dollars with some magnets and wire loops that aren't moving at all.
And when you combine these two totally unrelated static measurements,
You get the speed of light exactly. This was the proof that light is an electromagnetic wave.
but then the paradox just slaps you in the face. If light is a wave, what's the medium? In what special frame is this speed city fixed down?
Well, following the paradigm, everyone just assumed there had to be a medium. They called it the luminiferous ether, an invisible, rigid, all-pervasive substance that filled the entire universe.
So the speed city for Maxwell's equations had to be the speed of light relative to this ether.
Which means if the Earth is moving through this stationary ether, and it must be as it orbits the sun, then an observer on Earth should measure different speeds for light.
Depending on which way the light beam is pointing, right? Whether it's going with the ether wind, against it, or across it.
Precisely. And this is what led to one of the most important experiments in history, the 1887 Michelson-Morley experiment, the attempt to measure the Earth's absolute velocity through the ether.
Okay, let's walk through this setup because its cleverness is just fantastic. They used an interferometer.
Right. A light source shoots a beam at a half-silvered mirror, a beam splitter. Part of the light goes down one arm of length, the $1, the other part goes down a perpendicular arm of length, 22.
They both hit mirrors at the end, come back, and recombined at the beam splitter.
And when they recombine, they create an interference pattern. You see these bright and dark fringes. And that pattern is exquisitely sensitive to any difference in the travel time of the two beams.
And the whole prediction was based on this analogy of swimming in a river, right?
Exactly. If one arm of the device is aligned with the Earth's motion through the ether, the light going out is fighting a headwind of ether, moving at speed CV dollars. On the way back, it has a tailwind, moving at $70.
Which means the round trip time along that arm is longer than the time it takes for the light in the perpendicular arm.
Correct. The math showed that the time difference would depend on the ratio VC2-2. Now, they couldn't just measure this once because they had no idea which way the ether wind was blowing.
So this is the brilliant part. They put the whole thing on a rotating slab of stone.
The clever trick. They rotated the entire apparatus by 90 degrees. This swapped the roles of the two arms. The arm that was going with and against the current is now the cross-stream arm and vice versa.
And this rotation should have produced a clear, measurable shift in those interference fringes.
A very clear shift. The sources here are specific. Given the size of their apparatus, they folded the light path up to get about 10 meters of travel. And the Earth's orbital speed, the calculation showed they should have seen a shift of about 0.2 fringes.
And their equipment was good enough to see a shift of just 0.01 fringes.
So the predicted effect was 20 times larger than their detection limit. They should have seen it, easily.
But they saw nothing.
A null result. A persistent, frustrating, absolutely solid null result. No matter how they oriented it, no matter the time of day or year, they could not detect any motion relative to an ether.
And this just broke physics. The result was so devastating that people started scrambling for explanations.
The sources outlined 4 major hypotheses that came out of this. The first was ether drag, the idea that the Earth just drags a little bubble of ether along with it.
So right near the surface, there's no wind to detect.
But that was quickly rejected. It couldn't explain something called stellar aberration, which is an observed shift in starlight that depends on Earth's velocity. So, no go.
Okay, what was the second idea?
That Maxwell's equations are wrong. Which was, a pretty desperate move. Those equations were just too successful, too well verified in every other domain.
So that leaves 2 possibilities. The first is, to me, the weirdest one. The Fitzgerald-Lorentz length contraction.
Yes, this was a mathematical fix. They basically said, What if motion through the ether physically squashes objects in the direction of motion?
So the arm of the interferometer pointing into the ether wind actually gets shorter.
Exactly. It gets shorter by precisely the right amount, a factor of Blate 1 V2C2, to perfectly cancel out the expected time delay. It explains the null result.
But it feels so ad hoc, like the universe is conspiring to hide the ether from us.
It's the ultimate conspiracy theory. It works on paper, but it feels like a patch, not a principle. And that brings us to the fourth and most radical idea, the one a young patent clerk named Albert Einstein latched onto.
He just threw the whole ether concept away.
He said, what if the ether is just a fiction? What if we take the null result at face value and say it's telling us something fundamental about nature? The speed of light, $t, is constant in all inertial reference frames.
And that single postulate solves the Michelson-Morley problem instantly, but it completely shatters everything else.
The moment you accept that $2 is invariant, you have to throw out Galilean relativity. Time and space can't be separate and absolute anymore.
Let's walk through that logic again slowly. In the classical world, time intervals are fixed for everyone, but distances can change depending on your motion.
Right. And since speed is distance over time, if time is fixed and distance changes, then speed must change. My thrown ball example.
But if the speed of light doesn't change,
Then something else has to give. If the speed, distance over time, is going to be constant for everyone, even though we all agree the distance the light travels is different,
then the time must also be different.
the time interval itself has to be frame dependent. Your clock and my clock do not tick at the same rate if we are moving relative to one another.
This forces us into time dilation. Let's use the classic thought experiment, the light clock. We've got our two observers, one on a train, one on the station platform.
Okay. Observer T is on the train. Their clock is a simple device. A light pulse bounces vertically between two mirrors a distance other apart. The time for one tick, delta TTOshi, is just that distance divided by the speed of light, nether chi or.
And that time, measured in the clock's own rest frame, is what we call the proper time.
Exactly. Now, observer S is on the station platform, watching this train, and its clock whiz by at speed, vever dollars.
So from the platform, S doesn't see the light pulse go straight up and down.
No. Because the clock is moving, S sees the light travel along a diagonal path. The light leaves the bottom mirror, and by the time it reaches the top, that top mirror has moved forward.
It's a longer path. A diagonal is always longer than the vertical side of a triangle.
And since Einstein's postulate says both observers must measure the same speed cc, the light has to take more time to cover that longer path.
So just using the Pythagorean theorem, you can relate the vertical distance, the horizontal distance the train moves, and that diagonal light path.
And when you do the algebra, you get the fundamental result, delta TS, delta TT does.
Where gamma, the Lorentz factor, is $1 the CT2.
And since phi is always less than 1, the denominator is always less than 1, which means gamma is always greater than or equal to 1.
So the time measured by the stationary observer, delta TSC, is longer than the proper time, delta TDT2. The moving clock is running slow.
From the perspective of the observer on the platform, yes, the moving clock ticks more slowly.
But this immediately brings up the famous paradox, right? The so-called twin paradox. Motion is relative. So from the perspective of the person on the train,
The clock on the station platform is the one that's moving, so the person on the train must see the station clock running slow.
how can they both be slower than each other? That sounds like a flat-out contradiction.
It sounds like one, but it's not. And the resolution forces you to realize just how weird this new reality is. The key is something called the relativity of simultaneity.
The idea that two events happening at the same time for me might not be simultaneous for you.
Precisely. Because you and I disagree on what now means at different locations, we can both consistently measure the other's clock as running slow within our own reference frames. The paradox only arises if you try to bring the clocks back together, which requires one of them to accelerate and change frames, breaking the symmetry.
Wow. Okay. So if time intervals stretch, something has to happen to space to keep T-polyon constant. This must be length contraction.
It's the other side of the same coin. Length contraction is the spatial consequence of time dilation. If I'm on the train with a meter stick, I measure its proper length 1 meter.
But for me on the platform, watching that meter stick fly by.
To measure its length, you have to mark the position of its front end and its back end at the same instant in time.
But we just established that we disagree on what at the same instant in time means.
And because of that disagreement on simultaneity, you will necessarily measure a different distance between those 2 points. The math shows the length you measure. Delta xs is the proper length divided by gamma. Delta xs is delta xt, gamma.
So since gamma is greater than 1, the moving ruler looks shorter to me.
Shorter, but only in the direction of motion. If the train is moving horizontally, it will appear squashed, thinner, but its height will be completely unchanged.
These effects seem so counterintuitive, almost like philosophical games. But the sources provide this incredible, rock-solid empirical proof. Cosmogenic muons.
This is where it gets real. Muons are, they're like heavy electrons. They're created way up in the atmosphere, maybe 15 kilometers up, when cosmic rays smash into air molecules. And they travel down towards us at nearly the speed of light.
And the key detail is their lifespan. They are incredibly unstable. In a lab, at rest, a muon only lives for about 2.2 microseconds. That's its proper lifetime.
Now, let's do the classical calculation. If a muon is traveling at, say, 0.99 C from 15 kilometers up, how long does it take to reach the ground? The answer is about 50 microseconds.
Okay, but its lifetime is only 2.2 microseconds.
So it's dead long before it gets here. Classical physics predicts that we should detect almost 0 muons at sea level. They should all decay high up in the stratosphere.
And yet, we detect them all the time.
Yeah.
Our detectors on the ground are constantly being hit by these muons. So what's going on?
Time dilation. From our perspective here on Earth, that muon is a tiny, fast-moving clock, so its internal clock must be running slow.
Let's run the numbers from the source. At 0.99 C, the gamma factor is about 7.1.
So we on Earth see the muon's lifetime as being dilated, stretched out. It's not 2.2 microseconds for us, it's 2.2 times 7.1, which is about 15.6 microseconds.
Okay, 15.6 microseconds. That's a lot longer, but it's still way less than the 50 microseconds it needs to travel 15 kilometers, so they still shouldn't make it.
Ah, but you're still thinking from only one perspective. What does the universe look like from the muon's point of view?
Oh, right. From the muon's frame, it only lives for its proper lifetime, 2.2 microseconds.
Correct. But from its frame, the atmosphere is rushing up towards it at 0.99 C.
So the distance to the ground must be length contracted.
Exactly. The 15 kilometers is the proper distance in our Earth frame. The muon measures that distance as being contracted by a factor of gamma. So for the muon, it only has to travel 15 kilometers divided by 7.1, which is just over 2 kilometers.
It can easily travel 2 kilometers in its 2.2 microsecond lifetime.
The beauty is that both frames of reference give the exact same correct answer. The Earth observer uses time dilation to explain the muon's survival. The muon uses length contraction. Both predict we'll see them on the ground.
And the sources have the actual data. They detail an experiment measuring muon counts at different altitudes.
The graphs are just stunning. The non-relativistic prediction is this exponential curve that just plummets. The relativistic prediction is a much shallower curve, and the actual data point.
They lie right on the relativistic curve. It's a perfect fit.
It's not a small effect. It's a difference of orders of magnitude. The data shows an experimental gamma factor of around 6.3, corresponding to a speed of about 0.987 C. It's direct, real-world proof that the universe operates on relativistic rules.
So the data is undeniable. Time and space really do stretch and shrink. So now we need the formal mathematics that connects them. We're moving from Galileo's simple rules to the much more complex Lorentz transformation.
Right. The Lorentz transformation is the engine of special relativity. It's the set of equations that tells you how to convert the coordinates of an event, t, x, y, z, z, from my frame to yours.
And the whole thing is built from just 2 requirements, right?
Just 2. First, speed of light has to be the same for both of us. Second, at very low speeds, these new equations have to simplify back down to the old Galilean rules, which we know work for everyday stuff.
And the big takeaway is that space and time get mixed up.
Mm-hmm.
My new time coordinate depends not just on your old time, but also on your position in space.
That's the relativity of simultaneity in mathematical form. It means we can't think of space and time as a separate stage in a universal clock anymore.
Mm-hmm.
They are woven together into a single, 4-dimensional fabric, space-time.
How you slice that fabric up into space and time depends entirely on how you're moving through it.
And to visualize this, physicists use space-time diagrams. They're incredibly useful.
So you plot time, usually scaled by $20, on the vertical axis and 1 dimension of space on the horizontal.
Right, and any single point on that graph is an event. The path an object takes through space-time is its world line. If you're standing still, your world line is a straight vertical line. You're only moving through time.
If you're moving, your world line is tilted. The faster you go, the more it tilts toward the horizontal.
And if you're a particle of light moving at the maximum speed, your world line is a 45-degree line. Those 45-degree lines form the light cone, which is the absolute boundary of causality.
Anything inside my past light cone could have affected me now. Anything inside my future light cone is where I can possibly go or send a signal.
And anything outside that cone is space-like separated. It's fundamentally inaccessible. You'd have to travel faster than light to get there, which is impossible.
Now, in regular 3D space, we have this idea that distance is invariant. If I rotate my coordinate system, the distance between 2 points doesn't change. Is there an equivalent for space-time?
There is, and it's the mathematical heart of the theory. It's called the space-time interval, delta S22.
And it's defined as delta S2 plus delta by 2 plus delta Y2 plus delta Z22.
That's the one. And even though you and I will disagree on the time separation, delta T, and the spatial separation between two events,
We will always agree on the value of that combination, delta S22. It's invariant for all observers.
and notice that crucial negative sign in front of the time component. That's what gives space-time its unique geometry. It's not just four-dimensional Euclidean space. That minus sign fundamentally separates time from the three space dimensions.
Okay, so to handle this new four-dimensional world, we need a new kind of mathematical tool. This is where four vectors come in.
Exactly. Since an event needs four numbers to describe it, we package them together into a single object, a four-vector. The most basic one is the four displacement, which is just the four coordinates of an event.
This is also where we get into that notation that can be a bit intimidating. The upstairs and downstairs indices, contravariant and covariant. Why is that necessary?
It's a great question. It's basically a bookkeeping system to make sure physical laws are written in a way that is Lorentz covariant, meaning the equations have the same form for all inertial observers. In the flat spacetime of SR, it might seem a little like overkill, but it becomes absolutely essential when we get to the curved spacetime of general relativity.
So it's about making sure the math correctly reflects the underlying geometry.
You've got it. It ensures that when we calculate things that should be invariant, like rest mass, the result is truly independent of the reference frame.
And if space-time itself is structured this way, then our old laws of physics, like Newton's definitions of momentum and energy, have to be rewritten to fit this four-vector structure.
They absolutely do. The classical momentum math BFP just doesn't work. If you use it, you find that momentum isn't conserved in all reference frames. The fix is to multiply it by the gamma factor.
So relativistic momentum is math equal count BFP.
And that simple change makes momentum conservation a universal law again. The same logic applies to energy, which gives us the most famous equation in all of physics.
1 in C equals CP2, or rather equal gamma MC22.
That gamma is crucial because if we look at what that equation means for slow-moving objects, something amazing appears. We can do a Taylor expansion.
And the sources show that the energy approximates to 1 proxim Z2 plus Fray 1 P2.
Right, and that second term, Fray 122, that's just the old Newtonian kinetic energy. But look at the first term.
It's a new form of energy that an object has even when it's not moving. It's rest energy. The energy an object possesses simply by having mass.
So energy and mass are two sides of the same coin. They're interchangeable.
They are, and just like we had the invariant space-time interval, there's an invariant quantity that combines energy and momentum.
The form momentum.
Right, and its invariant length gives us the full energy-momentum relation. $2 is math BFP 2C2 plus Metal 2 C4 doer. This single equation governs everything from a slow-moving baseball to a massless photon. To really drive this home, the source uses a great thought experiment: the inelastic collision of two lumps of clay.
This one is so good because it shows that mass itself is not conserved. We imagine two identical lumps of clay, each with mass dollars flying towards each other at the same speed. They collide head-on and stick together, forming one big stationary lump of mass dollars.
Classically, you'd just say 1 LR use 2 Millers, conservation of mass.
But relativistically, we have to conserve total form momentum, which means we conserve total energy. The initial energy is the sum of the two moving lumps' energies, so $2 times gamma MC22. The final energy is just the rest energy of the big stationary lump, 1 C22.
So if you set those equal, the C22 terms cancel out.
And you're left with 1 molar is greater than 2 molars. And since gamma is always bigger than 1.
The final lump of clay is heavier than the sum of its parts. 1 Ollars is greater than 2 Ollars.
Yes. That initial kinetic energy of the two lumps didn't just disappear. It was converted into internal energy heat, mostly. And that internal energy contributes to the rest mass of the final object.
So if they hit at, say, 60% of the speed of light, where gamma equals 1.255 fines, The final mass is 2.05 mol, a 25% increase in mass created purely from the energy of motion.
Mass is energy, and energy has mass. It's a profound, unavoidable conclusion.
Okay, so special relativity gives us this beautiful, self-consistent picture of a universe without gravity. But the moment you introduce gravity, the whole thing starts to break down. We have to say goodbye to these nice global inertial frames.
We do, and the source points out a couple of key contradictions. Let's start with gravitational redshift. We know from experiment that if you send a light wave upward, away from the Earth, its frequency decreases. It gets redshifted.
It loses energy as it climbs out of the gravitational well, just like a ball I throw in the air slows down.
Exactly. A photon's energy is tied to its frequency, so it must lose frequency. But in the flat spacetime of special relativity, if I have two observers, one at the bottom and one at the top, who are stationary relative to each other,
Their world lines should be parallel. The wave crest should remain equally spaced. There should be no frequency shift.
so SR predicts no redshift, but experiments show a redshift. That's a fundamental contradiction. It proves that spacetime cannot be flat in the presence of gravity.
And the other attempt to shoehorn gravity into SR, trying to treat it as just a form of constant acceleration, that fails too.
That fails spectacularly. You can model a uniformly accelerating elevator in dip space using SR, but you can't model the Earth's gravity that way. Why? Because gravity is radial. It points to the center.
So an observer at the North Pole says up is in one direction, but an observer at the equator says up is in a completely different perpendicular direction.
And yet those two observers are at rest relative to each other. You can't describe that situation with a single uniform acceleration. It just doesn't work. We need something much more radical.
And that radical idea is Einstein's principle of equivalence.
This is maybe the single most brilliant insight in the whole story. Einstein realized that the reason inertial mass, the m in EFMA, is exactly equal to gravitational mass, the m in the law of gravity, isn't a coincidence. It's a deep truth about nature.
It means that gravity is, in a sense, an illusion.
Locally, yes. If you are in a freely falling frame, an elevator with the cable cut, gravity vanishes. You and everything else in the elevator float. You feel weightless. In that small local region, you are in an inertial frame, and the laws of special relativity apply perfectly.
So the freely falling frame is the local substitute for the old global inertial frame.
Exactly. But it only works locally. Gravity hasn't really gone away, and you can tell because of tides.
Right. If my freely falling elevator is very large, I'll notice that two balls on opposite sides will start to drift towards each other.
Because they are both falling towards the center of the Earth along radial lines, and those lines converge. That differential pull, that tidal effect, is the true signature of gravity. It's the part you can't get rid of by jumping in an elevator.
And that convergence of initially parallel lines, that's the definition of a curved surface.
That's the key insight. The fact that initially parallel world lines of freely falling objects eventually converge or diverge proves that spacetime is not flat. It is curved. Gravity is not a force that pulls things through spacetime. It is the curvature of spacetime itself.
And objects just follow the straightest possible path through this curved spacetime.
They follow geodesics. And just like in SR, those geodesics are the paths that maximize the proper time that elapses on the object's own clock. The principle of maximum aging still holds.
So this leads us to the grand equation that describes it all. The Einstein field equation.
The EFE. It's the mathematical expression of this dialogue between matter and geometry. On one side of the equation, you have the geometry of space-time,
Which is described by the metric tensor. If flat spacetime had a simple, rigid ruler, curved spacetime has this flexible, dynamic ruler that tells you the distance between points everywhere.
And on the other side of the equation, you have the source of that curvature. In Newton's theory, the source of gravity was just mass. But in relativity, it has to be all forms of energy and momentum.
This is the stress-energy tensor. It includes energy density, momentum, pressure, stress, everything.
And the equation just says geometry equals source. Matter and energy tell spacetime how to curve.
And the curvature of spacetime tells matter and energy how to move. It's a beautiful, dynamic, and incredibly complex feedback loop.
Okay, so with the field equations in hand, we can start looking for solutions. The simplest one, the spacetime outside a single static spherical mass, is the famous Schwarzschild metric.
It's the vacuum solution, where the stress-energy tensor is 0. And it immediately gives us back the things we knew had to be true, like clock slowing.
Right, it predicts that a clock closer to the mass will tick slower than a clock far away. It mathematically confirms that gravitational redshift.
And it predicts the existence of something completely new and bizarre, a point of no return, The event horizon.
This happens at a critical radius, the Schwarzschild radius. 3 of Essence include 2GMC22. If you can squeeze a mass knowledge down into a sphere smaller than this radius, you form a black hole. The escape velocity at that radius becomes the speed of light.
So what does that mean for someone watching from far away as, say, a spaceship falls towards one?
It's a tale of two perspectives. For the distant observer, the light from the spaceship becomes more and more redshifted as it gets closer. Its clock appears to tick slower and slower. As it approaches the event horizon,
It seems to freeze.
it asymptotically approaches the horizon, fading and redshifting away, but it never, ever crosses it in the distant observer's time. The journey takes an infinite amount of their coordinate time.
But for the astronaut in the spaceship,
The experience is completely different and very finite. They feel no particular bump or barrier as they cross the event horizon. Their own clock ticks normally. They pass through in a finite amount of proper time and continue on to the singularity at the center in a very short duration.
so the coordinate system of the outside observer just breaks down at the horizon.
It does. It can't describe what's happening inside. And inside, the curvature is so extreme that all possible future paths, all geodesics, point only one way, towards the singularity at $20. Escape is not just difficult, it's geometrically impossible.
Now, GR also has profound things to say about orbits, which are very different from the Newtonian picture.
Oh, yes. Newton's gravity allows for stable circular orbits at any distance from a star. But the Schwarzschild solution imposes a hard limit. Stable circular orbits can only exist for radii greater than 3 MC/MC42.
That's the innermost stable circular orbit, or ISCO. What happens inside that radius?
There are no stable orbits.
Yeah.
Any object that drifts inside the ISCO, even if it's trying to orbit, is doomed. It will make a few more spirals and then plunge directly towards the black hole. You can't stay up.
We actually see evidence of this in the accretion disks of matter swirling around black holes.
Absolutely. And GR also solved one of the biggest nagging problems in astronomy, the precession of Mercury's orbit.
Mercury's elliptical orbit isn't fixed in space. The whole ellipse slowly rotates or precesses around the sun.
And while the gravitational tugs from other planets like Jupiter explain most of that rotation, there is a tiny, stubborn leftover, a discrepancy of 43 arcseconds per century that Newtonian physics just could not account for.
It was a huge mystery for decades.
And when Einstein applied the first correction terms from his new theory of gravity to the problem, the math predicted an extra precession of exactly 43 arcseconds per century.
He must have known he was right at that moment.
It was one of the first and most powerful confirmations of the theory. It explained a known anomaly with no new fudging or free parameters.
The theory also predicts that light itself can orbit. This is the photon sphere.
At a radius of exactly 200 to the 4 equals 3 GMC in a 2-2, gravity is so strong that it can bend light into a perfect circular orbit, a ring of light trapped in orbit around the black hole.
And this is what the Event Horizon Telescope is actually imaging, right? Not the black hole itself, but the silhouette of the hole against the light from that region.
You're seeing the shadow cast by the event horizon onto the bright emission from gas and the gravitationally lensed light from around the photon sphere. It's an image of curved space-time itself.
It's incredible. And to bring it all full circle, GR predicts gravitational waves, which we detect using another interferometer.
It's a beautiful symmetry, isn't it? If you have something dramatic happen, like two black holes spiraling into each other and merging, it creates a ripple in the fabric of space-time, a gravitational wave.
And these waves propagate outwards at the speed of light.
And when a wave passes through Earth, it subtly stretches space in one direction while squeezing it in the perpendicular direction.
So you have a huge Michelson interferometer, like LIGO, with arms that are kilometers long.
The wave makes one arm temporarily longer and the other temporarily shorter. This changes the light travel time, messes up the perfect interference pattern they've set up, and creates a tiny flicker of light at the detector.
The detection of gravitational waves was the final stunning confirmation of a prediction made 100 years earlier.
So we've seen how GR describes gravity around stars and black holes, but what about the entire universe? For that, we need cosmology and the Friedmann-Robertson-Walker FRW metric.
This is the metric that describes a universe that is, on large scales, the same everywhere and in every direction.
Right. It's a simpler geometry, but one that changes with time. The key ingredient is the scale factor. It's a number that tells you the relative size of the universe at any given time.
So if AT doubles, the distance between any two distant galaxies also doubles, The universe is expanding.
And that expansion is what causes the cosmological redshift we see. As a photon travels across the expanding universe, its wavelength gets stretched along with the fabric of spacetime.
So the more the universe has expanded during the photon's journey, the more its wavelength is stretched, the redder it appears.
Exactly. The redshift is a direct measure of how much the universe has grown since the light was emitted. It lets us map the expansion history of the cosmos.
And the dynamics of that expansion, how TD changes over time, are governed by the Friedmann equation.
Which is just the Einstein field equation applied to the whole universe. It connects the expansion rate of the universe to its total energy density and its overall spatial curvature.
That curvature is described by a parameter, in tech dollars. It could be positive, negative, or zero.
If the dollars is positive, the universe has a spherical, closed geometry. It's finite and will eventually recollapse. That happens if the density is greater than some critical value.
If dollars is negative, it has a saddle-shaped open geometry. It's infinite and will expand forever. That's for a density less than the critical value.
And if tau is zero, the density is exactly equal to the critical density, and the universe is spatially flat, infinite, but with Euclidean geometry on the largest scales.
So which one is it? This is where the modern cosmic inventory comes in. We've measured the density of matter, and dark energy.
And when you add it all up, the results are just staggering. We use the parameter omega, which is the actual density divided by the critical density. Our measurements for matter and dark energy give us
A total omega of 0.9993 pm 0.001991.
which is, to within our ability to measure, exactly 1.
So the universe is flat.
The universe is, observationally, spatially flat. The total amount stuff in it is precisely the amount needed to make its large-scale geometry Euclidean. So we've taken this incredible journey. The simple, stubborn fact of light's constant speed tore down Newtonian physics, forced us to unify space and time, and then that unification led to a new theory of gravity as space-time curvature, which has been tested from muons to merging black holes to the entire cosmos.
And it ends on this beautiful, tidy observation. The universe is flat. Omega is 1. But like we saw with the Michelson-Morley experiment, whenever something in physics looks a little too perfect, a little too tidy, it's usually hiding a massive problem.
And this is one of the biggest. It's called the flatness problem.
Why is a flat universe a problem? It sounds like the simplest, most elegant solution.
It sounds elegant today, but the laws of cosmic expansion make it an unbelievable coincidence. In a universe filled with matter and radiation, like ours has been for most of its history, a flat geometry is an unstable state.
What do you mean unstable?
Think of balancing a pencil on its tip. Any tiny deviation from perfect balance will grow over time. The same is true for the universe. If the early universe had been just a tiny, tiny bit curved, if omega was 1.0000001, that deviation would have been magnified billions of times over by the expansion.
So if it started just a fraction denser than critical, it should have recollapsed into a big crunch billions of years ago.
And if it started a fraction less dense, it should be so wildly open and empty by now that galaxies couldn't have even formed. The expansion would have ripped everything apart.
So for it to be so close to perfectly flat today, after 13.8 billion years of expansion,
It must have started out flat to an insane degree of precision. The sources calculate that at the very earliest moments of the universe, omega must have been equal to 1 to within 1 part in $10.
1 part in 10 to the 60th power. That's not a coincidence. That's impossible. That's a level of fine-tuning that just screams out for a physical explanation.
It suggests that the universe wasn't just born flat by chance. Something must have happened very early on to actively force it to be flat.
And this is the primary evidence for the theory of cosmic inflation.
Exactly. The idea is that in the first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated exponential expansion. This inflationary epoch would have taken any initial random curvature and stretched it out so violently that the universe became, for all intents and purposes, perfectly flat.
So the flatness we measure today isn't a finely tuned initial condition. It's the generic expected outcome of a physical process that happened right at the dawn of time.
That's the provocative thought. The shape of our entire cosmos today might be the fossilized evidence of the most violent event in history, a moment of cosmic inflation that set the stage for everything that followed.
From a single constant speed to the very shape of reality. Always more to learn. Thank you for joining us for this deep dive.